In one of my previous videos, we talked about the fact that all substances can be kind of categorized either as simple or giant, and the giant ones could be giant covalent, giant metallic, or giant ionic. If though you've got a small group of, or a group of non-metal atoms bonded together, always non-metal atoms, they have a simple structure, and we'll talk about what that means in a second, and they'll be bonded together by covalent bonds. And the first thing you should know really is the definition of covalent bonds, and another definition, this word molecules. So if you see the word molecule, or we'll talk in a bit about intermolecular forces, this only refers to when you've got these simple covalent substances, things like water, hydrogen, carbon dioxide, oxygen, and so on. But the definition of a covalent bond is when you've got, this is one to learn, so learn this definition, could be worth a couple of marks, is when you've got a shared pair of electrons, so shared for a mark, pair of electrons between two nuclei. So what's going on, why does that happen, and how do we kind of draw that and represent that is what we're going to get to. But I'll first of all just remind you that simple covalent substances are substances which might be something like hydrogen, like this, and they are not in these large giant array structures. What you've got, I'll just draw it down here, what you've got is molecules like H2, or it could be H2O, and another one over here, and another one over here, and another one over here. Those molecules are not strongly bonded to each other. They have quite weak attraction between the molecules, and that weak attraction we call intermolecular forces. Those intermolecular forces are much weaker than the strong covalent bonds between the hydrogen atoms, or between the hydrogen and oxygen atoms in water, say. And when you boil water, you boil hydrogen, you boil oxygen, you boil ammonia, and you boil one of these simple covalent substances, you don't break the strong bonds within the molecule. What you break is the weak intermolecular forces. So you would say, for properties of simple covalent substances, that they have low boiling points because they have weak intermolecular forces which require little energy to break. So there is that definition for copying, or for putting on a flashcard or something. They've got low boiling points, weak intermolecular forces between the molecules which require little energy to break. And people find the concept of this quite difficult, because people think that when you boil water, the bonds within the water break. They don't. You simply break, or overcome, overcome might be a better word, you simply overcome these dotted lines, these weak intermolecular forces. Then you end up with water molecules that are completely separate from each other. They're now in the gas phase, they're not held together. There we go. Okay, so how do they happen, why do they form? And so what you've got, sometimes we represent a covalent bond with a straight line like that, and that straight line is representing two electrons, and you'll see in a bit sometimes we have two lines or three lines, and they're representing 4 or then 6 electrons. So each line is 2 electrons. We can represent them like this, which is the common way that we'll draw them when we need to practice drawing molecules, dot cross diagrams like this. But what's going on is, you wouldn't draw this in an exam, so this is just for information really, is to show you that this shared pair of electrons, a pair of electrons representing these dot and cross here, between two nuclei. So the nuclei of each hydrogen atom are positively charged, and the hydrogen atoms are held to each other by these negative charges. So chemistry is really always about electrostatics, electrostatic attraction and repulsion, but here we've got electrostatic attraction between the nucleus of one hydrogen and the electrons between them, and this positive nucleus and these electrons. It's all kind of being held together that way. Okay, so in all likelihood you're going to have to be able to draw a dot cross diagram in your exams, and there's a number of molecules that come up again and again. Now if you're asked to draw these, you could try and learn a whole load of them before you go into the exam, but it's much better just to work out how to do them, work them out on the fly. It'd be so much easier than trying to memorize them. So the trick with these is to know how many bonds each atom type makes, and it's always the same. So the way to work it out is that hydrogen has got 1 electron in its outer shell. It can get 2 in its outer shell, and therefore it's got space for 1 electron, therefore it makes 1 bond. Always. Hydrogen always makes 1 bond. Oxygen's in group 6. It's got space for 2 electrons, and so it will always make 2 bonds. Carbon's got 4 in its outer shell. It's got space for 4 more, and will therefore make 4 bonds. We call this the valency. 1, 2 and 4, the number of bonds it can make. Nitrogen is in group 5, so there's spaces for 3 more electrons, so it makes 3 bonds always. Chlorine and fluorine, both in group 7, which means they've got space for 1 more electron, which means they make 1 bond. There are some more unusual ones that appear occasionally. Sulfur's in group 6, just like oxygen, so it can make 2 bonds. Silicon, same as carbon's in group 4, and so it can make 4 bonds. So once you've got those numbers in your head, it then becomes really quite easy to draw the molecules. Now the first thing with this, and students that follow my guidance here, follow my recommendation that you do it this way, tend to do better. So I'd encourage you strongly to do that, please. And if you're asked to draw, say, water, the trick is to draw this line diagram to start with. Now what I mean by that is draw a line between the atoms. Oxygen we know makes 2 bonds and hydrogen makes 1 bond. So the only way water can be held together is like so. We do the same thing for methane. Methane is CH4. The only way to draw that as a line diagram is with carbon making 4 bonds and each hydrogen making 1. So that has to be what it looks like. So draw that on your exam paper, just somewhere in the corner, and then you can work out the dot cross diagram afterwards. I'll show you how to do that in a second. Ammonia, NH3, nitrogen makes 3 bonds, hydrogen makes 1. So it has to be that. It has to be. There's nothing else you could do. Oxygen, O2. Each oxygen makes 2 bonds, so the only way to combine them now is to make a double bond between those 2 oxygens. Nitrogen. Each nitrogen makes 3 bonds, so the only way to combine them together is to make 3 bonds. Okay, so here's some examples I'll work through, and I'll give you a few more to think about at the end. So going back to water, each line is representing 2 electrons. So now we draw the dot cross diagram like this, with 2 electrons in the shared and the overlapping space, like so. Right, that's 1 mark. And then remember that all atoms must have full outer shells. Once we're finished with this, hydrogen you can only get 2 in the outer shell, and 1, 2. There's 2 electrons in that outer shell now, so that's done. Hydrogen's done on both sides. Oxygen you can get 8 in total in the outer shell, and it had 4. 1, 2, 3, 4. So I've added 4 more, so it's got 2 more pairs of electrons, if you like. Same idea with methane. Draw the line diagram to start with. We know each line represents 2 electrons. And then you check to make sure all the atoms have full outer shells, which they do here. Hydrogen's got 2 and carbon's got 8, job done. Nitrogen, slightly more tricky example here. Nitrogen makes 3 bonds. Hydrogen makes 1. Each line represents a pair of electrons. Hydrogen's got full outer shells already, but the nitrogen's only got 6 so far, so we need to put 2 more in there. It doesn't matter if you draw dots and crosses, by the way, at GCSE, no one cares. Oxygen, again, slightly more unusual example than the ones above, because we've got 2 lines between them. Each oxygen must make 2 bonds, and 2 lines means we've got 4 electrons. We can draw 2 dots, 2 crosses if you want to do it in the usual way, but it doesn't really matter. But to make sure then they've got full outer shells, we have to have 4 more in each outer shell of oxygen. And that's so 1, 2, 3, 4, 5, 6, 7, 8. So that one's full and that one's full. Nitrogen, same sort of idea, this time with a triple bond. Draw them nice and big so I can fit 6 electrons in there. There we go, so that's nitrogen. I'm going to finish off with just drawing some more examples for you to try. So I've seen all of these in exam papers various times. Have a go at doing these. Pause the video now, have a go and see if you get them right. So at the top here, carbon dioxide, probably the most common question you'll see. Carbon must make 4 bonds, so 2 double bonds either side of the carbon. And then that carbon is full, no need for extra electrons, but you have to fill the electrons around the outside of oxygen. This question is often got wrong because people forget to put the extra electrons around the fluorine atoms. Apart from that, it's the same as methane. This one was quite difficult, a real challenge. You have to know the structure of ethanoic acid really to have a good chance of working out. I haven't drawn this well because I rushed it, but there's 4 electrons in there to represent those 4 electrons represented by those 2 lines. I've drawn them all as crosses in that particular example. Methanol here, that's the only way to represent that. I've done a mixture of dots and just crosses everywhere for some reason as well. Doesn't really matter. Hope that was okay. Last little point, simple covalent substances don't conduct electricity. I forgot to mention that anywhere. There are no free electrons, there are no ions present, so they don't conduct electricity. That's it.